Today we are going to discuss work and power. In this we'll first start with what is work. Then what are the different expressions for finding work. We'll also discuss how we can find work for a constant force and how we find work done when there is a variable force acting there. And after that we'll also discuss what are the positive work, negative work and zero work. And finally, we'll discuss some numericals based on this topic. So let's start with work. Now, for work, we define work as it is said to be done when force displaces a body through some distance in its direction. In fact, it is basically, you can say that it is given by the scalar product of force and displacement. That you can treat as the basic starting expression for finding work. So work done, we take it as a dot product of force and displacement. But remember, this we use when there is a constant force acting there. So this is there for constant force. Or you can use another expression for work done when the variable force is acting there. So for that, we take this as a scalar product of force and elementary displacement and we integrate it. So it is basically integral of force and displacement and they are basically dot product. So this is the expression for variable force. So W equals to integral F dot ds. This is the expression for work done when there is a variable force acting there, and W equals to Fs there for constant force. Now let's take this basic expression. W is F dot S. As it is the dot product, in that case we can write this as your Fs cos theta. So here we have force and displacement and theta is the angle between the two. Like if you have suppose force here and this is the displacement and the angle between the two is theta. So basically we'll have to find the component of this displacement in the direction of force, or you can also take component of force in the direction of displacement. Because if this is your F dot S, we write it as your Fs cos theta. Suppose I take a perpendicular and we drop it like this. That means this expression will be how much? This is your F cos theta. So this one can be written as your F cos theta into S. That means this is the component of force in the direction of displacement. So it is basically the product of the two, component of force in the direction of displacement. Or what we can do, we can drop perpendicular even from this one, that is S on the direction of force. So this term will be your S cos theta. So if you consider this W, which was your Fs cos theta, that means this is now the component of the displacement in the direction of force. So this basic thing you can remember and it will help you in finding work done in some special cases there and some complex also when you have to find the work done. Many times you'll find that it will be easier to take the component of force in the direction of displacement and you can take the product of the component and the displacement. In some numericals, you may find that it is easier to get the component of the displacement in the direction of force, and in that case you can take the product of the force and the component of the displacement in its direction. So you can use this expression for finding work done there. As we have the expression for work done given as W equals to Fs cos theta. Now you see that if theta is different, then cos theta value will be different there. That means we can take theta if it is acute, then cos theta will be positive. If theta is obtuse, in that case cos theta term will be negative. Or if theta is 90, in that case cos theta will be 0 there. Now, if you get for acute angle cos theta as positive, we define this work and classify it as positive work. Similarly, if theta is obtuse, you will get cos theta negative, so work done will become negative. So we say that there is a negative work. Similarly, if you consider that theta is 90, in that case the work done will be 0. So we say that it is the 0 work. So we take suppose positive work. So positive work when we are getting? When the angle between the force and displacement is acute. So work done is taken positive, or you can say positive work is said to be done when force makes acute angle with the direction of displacement. So if that angle is acute, in that case you will get work done as positive. In fact, what will be the example of such? If you are pushing an object, in that case work done will be positive. So here, for example, work done in pushing an object, this will be taken as the positive work. Why is it so? Because cos theta is positive for acute angle, so W will be positive. Similarly, if you consider negative work, so negative work is said to be done when force makes obtuse angle with the direction of displacement. That means here we are taking that theta is obtuse, so cos theta will be negative and hence work done will be negative. Now here when you get this type of case, suppose there is a body and its displacement is this side, we are applying force in this direction. That means the body was already moving in this direction there and we are applying force in this direction. So here the angle is obtuse. So in this case work done by this force will be negative. Or you take an example that you have a body and you are moving the body in this direction and there is a force, that means displacement is in this direction. Force of friction, if you consider, it will be in opposite direction there. So the work done by friction will be negative. So friction will be doing negative work there. Okay, so for this one you can take work done by friction. This will be negative. Or if you are pulling a body there and the body is moving in opposite direction there and this angle is obtuse, then also the work done by this force will be negative. Thirdly, we can take zero work. So when the force acts in perpendicular direction to displacement, work done is 0. Like here, suppose you have a body and we are moving a body in the horizontal direction. This is suppose the displacement. If you consider the force due to gravity, that is its weight, if you consider this is acting in this direction, perpendicular direction, the work done by gravity will be 0. So here work done by gravitational force is 0 when body moves in horizontal direction. Or even if you consider the work done by normal reaction. Normal reaction is also perpendicular here when the body is moving in the horizontal direction here. So work done by normal reaction also will be taken as 0. Or suppose you take a body which is moving in a circular path. The body is moving in the circular path. So there is a force, that is the centripetal force acting directed towards the center, and body will be moving tangentially at all points there. So here again, if you consider the angle between the two, that is the displacement or the velocity, if you consider, it will be 90 degree at all different positions. Like if it is here, velocity will be in this direction, displacement will be tangential there. Again, the force will be directed towards the center. So work done by this centripetal force will always be 0. So work done by centripetal force is 0 in uniform circular motion. So in that case, work done will be 0 there. What is the unit of work? Unit of work we take as joule in SI system. Okay, so it is your joule. Now, how we get that? W is your Fs cos theta. So if we consider that F is 1 unit, S is 1 unit, and theta is 0, that means cos theta is also 1. So then W will be equals to 1. So that means this one is your joule, because if you have taken, suppose in a SI system, in that case it is Newton, this is a meter, and this one will be your 1 there if the force is displacing a body through 1 meter there. So it will be 1 unit. So if you suppose want to define joule, then we say that 1 joule of work is said to be done when a force of 1 Newton displaces a body through 1 meter in its direction. Exactly in its direction if you take, that means the angle between the two will be 0 degree there. So then we take work done as 1 joule. And this is how you can define 1 joule also. Next term is power. It is the rate of doing work. That means power, if you consider, it will be basically work done by time taken. So it is the work done by time taken. So it is your W by T. So with that you can get work done there and divide it by the time so that you can find what is the power developed there or power consumed. Now, suppose if it is a general case given that body is moving from this position to this is the force acting there, find the power developed, you find out what is the work done and in how much time that work has been done. So work done by time will give you the expression for power there. In some cases, it may be given there in terms of the force and velocity. Now here you see that work done, we can take it as the dot product of force and displacement and we are dividing by time. So this can be written as your F dot S by T. Now this S by T, displacement by time, it is basically a velocity term there. So this is your F dot V. It means power you can also get as the scalar product of force and velocity. So with this also you can calculate, especially in any numerical, if it is given there that force expression is there, velocity expression is given and you have to find power. In that case, you can use this expression. If work expressions or data is given, time is mentioned, use the formula work done by time to find power. Then the unit of power. This is your watt. Basically, it is your joule per second. Work done per unit time, so it is a joule per second and that we call it as the watt. So here, watt will be the SI unit and the bigger units are your kilowatt, megawatt, okay, even horsepower. And 1 horsepower, you know that 1 horsepower is 746 watt. So this is how you can get the definition of the power, you can get the unit of power, expression for power. Okay. In this, for power, there is not any separate derivation or expression there. You have to only find the work done and divide by time or take the dot product of force and this velocity there. Let's now take work done in lifting a body through certain height. So we are taking work done in lifting a body through certain height. So suppose m is the mass of the body which is lifted through height h. This is h. So its weight is mg acting downward. So the force which is required to lift the body, that will be force required to lift the body. That will be equals to mg. Remember, this is the minimum force required because any amount of force more than this will be giving you accelerated motion. So this will not give you the work done in just lifting the body, that we want to find the minimum work done. So here this F is equals to mg. And now when the body is lifted through h, in that case work done W will be your F into h, force into displacement, because the angle between the two, that is 0 degree here. So in that case it is your mg into h, or that is equals to mgh. So this work done will be mgh. This is the work done in lifting the body through height h. But remember one thing, this is applicable only for small values of h. Why we are saying that? because only for a small height you can treat g to remain constant there, because you know that acceleration due to gravity varies with height. So if we consider that the distance through which it has been lifted is very large, over which there is a variation in g which we cannot neglect. So in that case, what will happen? This force will no longer will remain constant there, because we have directly used the formula force into displacement, assuming that this force remains constant there. So in that case, the work done will be not correct one if g is varying. So for this one, you remember and you can note it there that this expression is applicable for a small h only, over which g remains constant. When you do the acceleration due to gravity variation there, or basically in the gravitation chapter, you will find out the work done when a body is lifted through height h, where we are not neglecting the variation in g. So we can do the expression and find out what will be the work done in such cases. But here you just remember, if it is lifted through height h, which is not so large that we can consider the variation in g to be appreciable, in that case it will be equal to mgh. So this is the expression for work done in lifting a body through height h. Remember what we have basically done? We have taken a case where the force remains constant in the displacement of the body, and we have calculated the work done for that case. Let's now take work done in stretching an ideal spring. Suppose we consider that we have a spring here. It is attached to one end here. This is the fixed end, and its spring constant is K. We are pulling this spring by a force F, so that the extension produced is, suppose, X. So let K be spring constant of an ideal spring. Ideal spring, we take the spring for which we can consider its mass is negligible or it is light there, and whenever we apply force there, the force will be directly proportional to extension or compression produced there, and the moment we remove that, it will be acquiring the original configuration there. So here K is the spring constant of an ideal spring, and F be the force required to stretch it through X. So in that case, what will happen? F will be given as your K into X, because F is directly proportional to X, and K is the spring constant, that is the proportionality constant which is being used. So this is F equals to Kx. Now suppose we are pulling it there further, so let it be pulled further by dx. So a small work done dw, that will be your F dx, and if it is your F dx, this is your Kx dx. So if you want to find total work done, then we need to integrate this. So total work done when it is stretched through small a. So what will be the expression there? Total work done will be integral of this dw, which is your Kx dx integral 0 to L. So it is your Kx x square by 2, 0 to L. And that is your k by 2, L square minus 0, or half k L square. This is the expression for work done when the spring is stretched through L. So W is equals to half k L square. This is the expression for work done. Remember why we have gone for integration. In the earlier case, when the body was lifted through height h, we have not integrated that one. We have directly taken force and multiplied it by the displacement here. But here you can see that F is given as your kx. It means force is varying with x. That is the amount of extension produced or stretching which has been done there. So this force is a variable one. If it is a variable, so to find the total work done when it is a stretch through L, you cannot directly take the force and multiply it by displacement. You will have to integrate. You will have to find the change in the force there. Or how will you take that one? If it is your dx, it means we are taking a very small change in the length over which we can assume the force to be constant. So we have taken this as f dx. And then we have written the expression for force in terms of the change which is occurring there, or at a particular distance, or at a particular length, or a stretching if it is there. What is the force there? So that is your kx. Then we have integrated this one to find the actual variation in the force over the entire length. And then we can calculate the total work done. Let's now do some numericals or some questions there on work, so that the concept will be more clear there. Let's take first question. Suppose it is said that there is a body of mass m, and this body is being displaced through S. So S is the displacement of the body, and we have applied a force F there. So by applying a force, we have displaced the body through S. You have to, and this body has the mass m, we have assumed. You have to find, suppose, work done by external force. Another one is work done by gravitational force. And third, we are taking work done by normal reaction. So you have to find the work done in these cases there. So here, if you consider, if the body is displaced through S and F is the force which is acting there, which has made the body to move, in that case, for first case, work done will be your F into S into cos 0, because the direction of the force and displacement is same, so it is your Fs, because cos 0 is your 1. But when you take the work done there by gravity or the gravitational force, so it is your mg. Normal reaction is acting upward there, so it is your mg, and this is your normal reaction. So for second case, if you consider work done by gravitational force, so this will be your mg into S, but the angle between the two is 90. This angle is 90. So in that case, work done will be 0. You take the third case, work done by this normal reaction. This you have to find. So in that case, it is your n into S into cos 90 again. So this is again 0. So this is how you can get the work done by different forces there when the body is moved through some distance. Let's take another case. This is suppose second one. There is a horizontal surface and this is the inclined one. This is a smooth surface there. No friction is there. We have a body of mass m which is moved through a distance on the horizontal surface, and then it is moving down the inclined plane. We have moved this one by exerting some force, and the moment it is coming at this point, we have removed the force and it is just sliding down. You have to find work done by gravity in the entire motion. Okay, so if you consider work done by gravity, suppose I take A, B, and this I call it as C. So work done by gravity during the motion from A to B. Remember, the weight or the gravitational force will be acting downward and the body is moving in this direction. So in this case, A to B, it will be your mg into this length L into cos 90, and that is 0. But when the body is moving, work done by gravity from B to C. Okay, B to C motion you can consider when it is moving from B to C. Remember, the weight is acting vertically downward. L, it is in this direction. So you will have to find the component of that one in this direction. So what you could do, you find out what is the component there. So component of the force in the direction of the displacement. If you consider, if this angle is theta, it is 90 minus theta because this will be 90. So this component will be how much? It will be your mg sine theta. This is the component of the weight along the inclined plane. So now here the work done will be equals to how much? Mg sine theta. Length is your L. And now the angle between the two, it will be 0 because the displacement and the component of the force are in the same direction. So in that case, this will be equals to this into you can say cos 0, or that will be equals to mgl sine theta. So this is the work done by gravity when it is moving from B to C. Remember, normally we take a W equals to Fs cos theta. So there, and the F on the body, it will be the weight. It is asked work done by gravity. So in that case, many may think that it is the weight mg there, and they may apply the formula Fs cos theta as mgl cos theta, but it is not mgl cos theta because there the angle between the gravitational force or the gravity and the displacement, that one is not theta. Theta is the angle between the inclined plane and the horizontal. So once you try to find out that angle, which is 90 minus theta, then definitely you will get the same expression, because there you will be using mg into L cos, and what is that? 90 minus theta. If you consider the angle between this, so this one will be how much? It is sine theta, so it is your mgl sine theta. So if you substitute the angle correctly, you will get the same expression. But if anyone is not careful, they may make the mistake. Now one more thing you can consider here. One more way in which we can get the same thing here. Remember, when the body is sliding down the inclined plane, the weight is acting downward, mg. So if you have to find the work done when it is moving from B to C, we have discussed or defined work done as the component of the force in the direction of displacement, and take the product of the two, component and the displacement, or find component of the displacement in the direction of force and multiply it by the force. So far we have taken the component of force in the direction of displacement. If you now consider the component of the displacement in the direction of force. Force is in this direction. So the component of this L in this direction will be how much? This will be your L sine theta. If this angle is theta, the component of the force will be this. That is L sine theta. mg is already in this direction. So in that case, work done again will be your mg multiplied by L sine theta. So that way also you can get same expression. So you can get this expression by using either the basic definition W equals to Fs cos theta, change the value of the angle there according to the given condition. So there, if you take that as 90 minus theta, you will get this expression. Or you take the component of the force in the direction of displacement, take their product, you will get mg L sine theta. Or you take the component of the displacement in the direction of force, again you will get the same expression. So in any way you can try this. Let's take another one. If F equals to 3I plus 4J minus 5K Newton acts on a body, find the work done when the body is displaced through 3 meter in Y direction. Or second part is there, when it is displaced from R1 equals to I plus J minus 2K to R2, 3I minus 2J plus K cap. Or when it is displaced from 2, 1, 2 to 3, 2, 4. So three ways are there in which the displacement is expressed here. One, directly in terms of the displacement in the different direction. Other may be in terms of the position vector. Next may be the coordinates of the position vector. So let's see how we find that one. All units are there, SI units which is used. So for first case, if you consider given that F is 3I plus 4J minus 5K. Body is displaced through 3 meter in Y direction. It means the displacement, if I consider, it will be only 3J cap. Because it is 3 meter in the Y direction it is there. So because the X component, Z component will be 0. So work done, it is your F dot S. So this is your 3I plus 4J minus 5K dot 3J cap. So in that case, only the coefficients of the Y axis or coefficients of the J will be taken care and it will be multiplied. So will be 12, 4 into 3. Others will be 0 there. So it will be this much joule. Okay, because the 3 into 3, 9, I dot J will be 0. Only J dot J will be 1, K dot J will again be 0. So it will be your 12 joule. Second, let's take. It is being displaced from R1 to R2. So if it is being displaced from R1 to R2, if you represent that one as R1 vector, this is R2, delta R is the displacement there when it is moving from R1 to R2. So using the triangle's law vector addition, you have R1 plus delta R equals to R2. So delta R will be how much? R2 minus R1. So you will get that expression. So it is your delta R equals to R2 minus R1. You simply subtract. It is your 3I minus I, that is 2I. This minus this, that is minus 3J. Then K minus this is plus. So this is the expression. This is for delta R. So work done, that is your F dot delta R here. So this will be your 3I plus 4J minus 5K, and the dot product is there with 2I minus 3J plus 3K, and that is your 6 minus 12 minus 15. So this is minus 27 minus this, so it is your minus 21 joule. This is the work done because we have expressed all the data there in SI unit. So in that case, it will be this much. Let's take now third one. Coordinate of particular position is given. We can write the position vector Like if suppose it is given as your x, y, z. This is the coordinate of particular position of a particle there. Then its position vector, corresponding position vector will be given as xi, yj plus zk. So here also, if it is given as your 2, 1, 2, in that case R1 we can consider as 2i plus j plus 2k, and R2 you can consider 3i plus 2j plus 4k. It means delta R, that will be your R2 minus R1 vector, and that will be equals to I plus j plus 2k. Simply take R2 minus R1. So it is 3 minus 2, that is 1 here, 2 minus 1, 4 minus 2. And now work done, which is your F dot delta R. So in that case, this will be equals to F, which is your 3i plus 4j minus 5k, and you are taking its dot product with I, j and 2k. So in that case, this will be your 3 plus 4 minus 10, and that is minus 3 joule. So this is the expression for the work done. This is the next question. If F is equals to 7 plus 2x acts on a body, find the work done if the body is displaced from x equals to 2 to x equals to 4 meter. Force has different value for different values of x. It is depending upon x, so it is a variable force. So to find the work done, we'll have to integrate force and displacement product here. So it is integral of this f dx, and x will be varying from 2 to 4. Now f is your 7 plus 2x dx, and we are integrating from 2 to 4. So this will be your 7 dx. Dx integral will be your x. Limit is from 2 to 4. This is 2. X dx integral is your x square by 2. Again it is 2 to 4. So it is 7. 4 minus 2. 2 will get cancelled. So it is basically x equals to 4 square minus 2 square. So this term will be equals to 7 into 2 plus 16 minus 4, that is 12. So 14 plus 12, that is 26 joule. If this force is given in Newton, suppose, in that case this will be your 26. Let's take this question. If vector f is x square I plus 2y j cap, and this acts on a particle and displaces it from 1, 2 to 3, 4. This is the coordinate of the point between which it has been displaced. You have to find the work done. Now for this one, you see, earlier also we have done the expression for work done when a force is acting on a particle and it is displacing the body from one point to other, where the position vectors or the coordinates of the position it's given there. But this there the force was your constant force, like it was your 2 I cap plus 3 j cap, like that. But here the force is a variable one, and you have to find the work done between 2 points where the coordinates of the points are given. So how will you proceed for this one? Now here let's see that work done expression, we have got it as f dot ds vector integral, especially if the force is your variable one. So here what will take for force, we have this expression, but what will take for ds? See, suppose if any displacement is given there, which we take it as suppose your xi plus yj. This is suppose the displacement. If I have to find the elementary displacement, in that case ds vector will be how much? It will be your dx I cap plus dy j cap. Now you take help of this one. Here work done will be your F dot ds integral, and this will be your x square I cap 2y j cap dot, this is your dx I cap dy j cap. Now you see, if you take this one here, I dot I, that will be 1. It means basically this will be your x square dx integral, and here it is your j dot j, that will be 1. So it is your 2y dy integral. Other products like I dot j, j dot k, like that, they all will be 0 there. So it is only x square dx integral and 2y dy integral there. But here you see, when you have to put the limit, what will take as the limit there? This is your dx integral. So what is the variation for x coordinate? So it is from 1 to 3. So this limit will be 1 to 3. Here 2y dy is there. So it will be the variation in the value of y coordinate. So it is 2 to 4. Now you just do the simple integration and substitute the limit. This is your x cube by 3, 1 to 3, and this will be your 2y y square by 2, because it is your y dy integral, and it is 2 to 4. So this one will give you x cube, that it is your 1 by 3, it is your 3 cube minus 1 first term, plus this 2 and 2 will get cancelled, so it is basically y square. So it is your 4 square minus 2 square. This is the second term. This is your 27 minus 1. So this is equals to 1 by 3. It is your 27 minus 1. So it is your 26. And this is your 4 square, that is 16 minus 4. So this is your 12. So this is your LCM. If you take it is 326 plus 36. And this value will be equals to, this is the expression for the work done there. If force is given in Newton and displacement is there in meter, in that case work done will be equals to that much joule there. So this is how you can find out work done for the different cases there, and you have the numericals based on this work. If the numericals are there on power, in that case it will simply give you the time expression also, if work datas are given there to find out. So from that you can find work done and then divide it by the time taken. Or if suppose the expression for the force and the velocity is given, you take the dot product of that, you will get the expression for power.